Imagine you are floating in the dead of space. Everything around you is calm, silent, and visually normal, except you are drifting dangerously close to a black hole. Under standard conditions, light is the absolute speed limit of the cosmos. Nothing in the known universe moves faster than its 186,000 miles per second. As you drift closer, gravity overpowers that speed limit. This is the event horizon, a spherical boundary that swallows light whole. Once crossed, your fate is sealed. No thrust can reverse the trajectory. You are permanently locked into a one-way trip inward. So what exactly would you see and feel if you slipped past that cosmic point of no return? The event horizon marks the definitive edge of reality. Past this line, our conventional rules of physics and cause and effect cease to function. To understand the descent, we have to look at your fall not from your eyes, but from a friend watching in a nearby spaceship. This chart shows how extreme mass bends spacetime into a steep funnel. As you fall deeper, gravity warps time itself. Through time dilation, your friend would see your movements drag. Every second takes longer to pass relative to theirs. Right as you approach the very edge of the horizon, you would appear to slow down so much that your image would completely freeze in place from their perspective. But for you, looking out from inside your spacesuit, nothing seems out of the ordinary. You watch your own watch tick at a completely normal, uninterrupted rate as you fall. Your friend seeing you freeze is not an optical illusion. The temporal reality between you two is literally operating at two entirely different speeds. Time is a highly flexible dimension, dictated entirely by how close you are to extreme gravity. As you continue your descent past the horizon, the bizarre time effects give way to a violent physical reality. You are now subject to an astrophysical process called spaghettification. This diagram shows the gravitational differential. The downward pull on your feet is exponentially stronger than on your head. This unequal force overpowers your molecular bonds. You are violently stretched vertically, eventually reduced to a single-file stream of atoms. That stream is rapidly pulled toward the exact center of the black hole, the singularity. This is a coordinate where general relativity and everything we know about the physical universe collapses into a mathematical paradox. Because we cannot observe it, physicists are left with competing theories. It could be a point of infinite density where matter is crushed to nothing, or a gateway leading to another region of space. The singularity is the absolute limit of human science. It marks a location where mathematics stops working, rendering the core reality of a black hole entirely unknowable. If we zoom out from that microscopic collapse, we see these colossal objects playing a central role in the structure of the cosmos. A black hole does not wander the void hunting for matter. It only consumes objects that lose their orbital velocity or drift directly into its path. These objects act as massive gravitational anchors, providing the immense pull required to organize and hold billions of stars together in stable galactic rotations. By tracking how these central masses interacted with gas clouds in the early universe, scientists can see how black holes regulated the birth of the very first stars. Mapping these gravitational relationships allows us to calculate how chaotic matter first coalesced into organized galaxies. If you could build an indestructible probe, send it straight through the event horizon, and successfully retrieve its data, what is the one question you would want answered? Let me know in the comments below. Black holes are the necessary architects of our universe, providing the heavy foundations required for galaxies to exist and for reality as we know it to take shape.